going to be the diameter. Here in this case, I did not draw a diameter. I have just chord, plain old chord, CD. Everybody okay with that? Okay. Now, CD being the chord, usually what we would say is, it's a segment, so you can say CD and just put a bar over it. That would denote that it's just the segment piece. Okay? Now, that chord has what's called an intercepted arc. Here's what that means. The arc that it hits is the curved part here. Okay? So, chords have what are called intercepted arcs. So there's also this thing called arc CD that would have the curve over it. Okay? Now, one of the things that we did the other day when we talked about arc measurements, I don't know if you remember. Remember when we talked about what was called the central angle? The central angle was the angle at the center of the circle that hit the edges. The sides of the central angle were always made up of radii. Okay. So if I draw this real quick, here and here, this angle here would be my central angle. Are we okay with that? Now we know that these two guys are the same because they're radii. They always will be. Right? So if, let's say, angle A was 83 degrees, what would arc CD have to be? 83, right? Because that was the relationship between them. Okay? That still holds true. Now, what's going to happen today is that, excuse me, we're going to look at this chord, and if I keep the same length of the chord, and I move it somewhere else, what would that arc have to be? Why?
Because it's the same.
Because it's the same. Okay. That's the idea of what we're looking at here today. What's going to happen is, when you wind up with chords of the same length, or chords that are in fact congruent to one another, those chords have to run into the same amount of the circle. All right? They have to. It won't work otherwise. Now, that makes this part 83. Sorry. Would it change any if this got... I'm trying to rotate this without spinning it completely. Give me 1 second if I can see if we can do it. That's not going to work that way. Trying to rotate it without changing the size of it. There we go. Now, if I put this chord here, is the arc going to be still the same?
Yeah.
Pay no attention that's going on in the circle. It doesn't.
It's not.
It's not. It doesn't. It doesn't. You're seeing things. No matter where I put that chord, as long as it touches the edge of the circle, that amount of the circle will always be 83 degrees. Okay? It has to, because the circle's staying consistent. Or constant, excuse me. Right? So that's one of the things that we're going to talk about today. Chords that have, don't write all this junk down, it's stupid. If you've got circles that are congruent, if circles are congruent, they have to have the same what? Radius. If circles have the same radius, they have to be the same size, right? If they're in the same circle, wouldn't they have to be the same as well? So basically what happens is, if the chords are congruent, they're going to be the same, their arcs have to be congruent. Okay? So it goes to the same idea of those chords are the same in that first circle, make both those arcs the same measurement. One of them was 83, the other one has to be 83. It's going to be following a lot of tick marks. It's not going to be anything more difficult than that. There's no proof to any of this that you have to worry about. We could do all these things, all these proofs for how all this works. Goes right back into congruent triangles, side angle, side, that kind of stuff. But we don't get into any of that. It's easy, but no big deal. So basically what I'm getting at is, if the chords are the same, the arcs are the same. I guess not too crazy. So, here's where it gets really, really difficult. I know, but I have some faith. Not a lot, just some. Little. Don't be afraid. Don't be afraid. Gavin, we give him a hug, make sure he doesn't get afraid. Okay. So, are those two chords, IJ and GH, the same? How do we know that? Tick marks, right? Okay, and they're in the same circle. Good. So, it's good. Now, if the arc that hits GH is 100 degrees, what does IJ have to be? Was that frightening?
Yeah.
Shut up, nobody cares. That's really all there is to it. You okay? Are you just in awe of amazement that it's that easy? Okay. All right. Now, all right, let's take this a step further. Is it okay that these two chords are equal? So, no matter where I put this chord, if I place it anywhere else, it's still going to be the same, right? Okay. Now, what happens then, if I draw this, if I draw to the chord, and it's technically has to be equidistant, because if they're the same distance away, if they're the same size inside of a circle, they have to be the same distance from the center. Otherwise, it wouldn't work, right? And remember, when you measure distances, if I'm going to measure to the wall here, I'm not going to measure to the corner of the tape measure. I'm going to go square to it. I'm going to measure the straightest distance, the closest distance I can. So what happens is, if chords are going to be congruent, they're always equidistant to the center. Okay? If chords are going to be congruent, they're always equidistant to the center. Again, this boils back down to being able to draw this. What are those? What are the red segments? What are those called? Radius, right? They're a radii, all right? What do you know about radii within the same circle? They're always the same. So that means each one of these is the same, correct? Right? Now, if we know, let's see, where was it here? If we know that it's equidistant and perpendicular, chords are the same back on the other side, doesn't this red triangle then become isosceles? Which means these angles here have to be the same, don't they? Which means they have to be the same here. It is crazy. Now, what would this central angle have to equal?
100.
100. Because the angle here is 100, isn't it? We okay with that? Now, if this whole angle is 100, oops, sorry, I'm going to change that up here. If this whole thing is 100, what do these two base angles have to be? 40s. They both have to be 40. Okay? So far, so good? It is kind of messy. We're trying to move some stuff out. So as of right now, we knew that this whole thing was 100. If this is 90, this is 40, what do each of these two have to be? 50. So notice what's happening. You're getting a whole bunch of congruent triangles out of this. Okay? Yeah, all the triangle stuff comes back into play because you've got perpendicular, you've got equidistance, you've got radii that are all congruent, and so on and so on. There's a lot of information you can get out of these things just by quickly drawing a couple extra segments, because these are things that you know. Okay? So, like I said, the other one that we did here, if chords are congruent, then they are equidistant and perpendicular to the center. Okay. It's a lot of words for something that shows up really easy to see within a diagram. If chords are congruent inside of a circle, they have to be equidistant and perpendicular to the radius. Or not the radius, excuse me, the center. Okay. Not bad? Not really not. Okay. Let's see. Whoa, what? Sorry to get ahead. You all right? Waiting. All right. So, one more quick picture here. And I'll get you some examples. Circle, center-ish, and I'm going to draw one more chord. It's close enough. Actually, the center's off. It's about better. Okay. Now, let me ask you this. What is always going to be the longest segment you can draw inside of a circle? Diameter, right? Okay. So, if I look at this piece here and I try to figure out where my diameter might go, so it looks a little off. That's better, right? Now, if I take just a generic segment, obviously it might be longer than what the diameter is. What's pretty close? So if I'm going through this, watch what happens as my segment that I think is a diameter gets through the center. Now, we know that if it's a diameter, it splits the circle into what? Cuts it in half, right? Now, if it cuts it in half, what do you think it does to this if it's a diameter? Well, it has to be perpendicular, correct. It'll be perpendicular, and it cuts it in half. So what happens is, if a diameter is perpendicular, excuse me, if a diameter is perpendicular to a chord, it could bisect it. Okay. So if what happens then, if this is 7, what's that side? 7. If this whole thing is 110, take a wild and crazy guess what each of those two arcs have. Yep, that's it. Same idea. If you cut a diameter, if you cut a chord in half, you cut its arc into half. Okay. So what happens here is, if a diameter, I think I have it written out on the next slide here. The reason why this works, again, you can draw radii. You get this. You get reflexive going into here, so you get side, side, side right off the bat. That means that these two angles have to be the same, which means this angle that hits this arc has to be the same as this angle that hits this arc. And since these two sides are the same, that means these two arcs have to be the same, and so on and so on. All right. It all stems from very simple problems, or very simple theorems, if you will, for how this works. So in terms of words, and I think if I can shortcut this a little bit better, if a chord is the perpendicular bisector, then it's if one chord is a perpendicular bisector of another, then it has to be a diameter. So if the diameter is a perpendicular chord, it bisects it. Okay, that's the easiest one. Let's say this again. If diameter bisects a chord, it's perpendicular to it. It's really simple to work with these things. Okay. Should be pretty easy. So far, so good? Obviously, there's a little bit more to some of these things as we get into it. We can get into a lot of redrawing, a lot of Pythagorean theorem and stuff like that. I've actually done questions with this before with some trig you can get into. You can do some really easy 30, 60, 90 stuff with there. Eventually, what we're going to do is we'll work with the angles that come back to here and stuff. So we'll work with these angles here. There's other properties that occur with all of that. Angles go pretty quick after we figure out how these intersection pieces work together. All right. Let me show you some examples then. I think I have some easy ones to go through. Oh, I'm sorry. Oh yeah, we did that. Yeah. Let me show you what I was looking at. I used an old worksheet that we have to keep drawing pictures, so we can look at a couple of quick examples here. And I apologize. I had completely forgotten to the hole punch it, so it's not my fault. One more here. So if you need a hole punch, I've got one of those in the back. You know. I said, it's a 7. I know.
No. And you said,
Did I? What are you looking at? I actually see it. I apologize. I didn't eat it's good fun. It's good fun. So, real fast, when we're looking at this one here, I just wanted to kind of go through a couple of the examples that are on here, just to show you that as you're going through some of the algebra, you'll see that the algebra that we work on, or the numerical stuff first, how unbelievably quick and easy it is to work with them. For example, if you look at number, oops, forgot to mute that. If you look at number 1, when you look at number 1, we've got are the arcs the same? Yeah, as you would say. So are the chords the same? So if one of them is 9, what is the other?
9.
Woo! Okay. I have some faith, not much, but some. Are the all right? What is it? Explain it. Tell me out. Help me out here. What are they called? Yeah. Well, we don't know the chords are the same. We know the arcs are the same. So the arcs are the same, which means the chords that run into them have to be the same, which means the other one, the FG, has to be. The next one's a little bit weird. Then I'll just blow this up so you can see it better. Why though? But it doesn't say anything. So what you're looking for, figuring out what this segment is. Okay. Now that segment and this segment, they only run into one portion that's the same. Now let me ask you this. If I'm going from here to here, and then from here to here, is there overlap? Are you overlapping the same amount? So wouldn't those two have to be the same? That's the idea. What happens here, remember we did angle addition? Remember we did that angle addition with that leftover middle piece? I would say that if angles 1 and 2 are congruent to angles 2 and 3, doesn't angle 1 and angle 3 have to be the same? Because it shared this common middle ground. It's kind of like a reflexive piece. It's just the overlap. So yeah, that whole segment, that KM has to be 80 because it runs in the same amount, right? It would be 80. Okay. It's just a little weird way of looking at it. Oops. Okay. 8. Okay. Again, X, Y, that's easy. On 5, they're giving you central angle. If that's your central angle, what's the arc that you run into? 85. So that means that the arc here at SR is 85, which means the arc here at TU is go. Okay. I'm not there yet. How many degrees are in a circle? 360. And number 6, they gave you one section of it. They told you it's 100 degrees. So that means for arc BAC has to equal 260. Why? Correct. Everybody hear that? These two arcs, BA and CA, have to be the same because the chords that make them are the same. So if you know that how many degrees are left over, you just cut it in half and you end up with 130. Okay. You'll notice the numerical version of this stuff is really easy. And we'll talk about the algebra stuff here in a minute. The next grouping just kind of gets you into whether or not it's a diameter. Remember, if it's going to be a diameter, it's going to be the perpendicular bisector of a chord. So in 7, is QS the perpendicular bisector? Yeah, because it's perpendicular and there's tick marks. In 8, no, because 19 doesn't equal 20, even though it's perpendicular. Okay. What about 9? Yes, it is a yes. They're congruent segments, and then if you look at your angles, the two angles, even though they don't have a square there, you know they're supplementary, and if two angles are congruent that are supplementary, they have to equal 90 each. Okay, so it still works. Going into the next grouping, LK and KN. Is there any way to know that MP is a diameter? There's no way of knowing that MP is a diameter. You'd have to have a dot somewhere in there to show that it went through the center. So there's no way to tell if in fact those two segments would be equal. Right? But with, what about, what is it, ST and RS? We have a diameter, but does it say it's perpendicular? But does it say it's perpendicular on 11? So there's no way of knowing. You can have a diameter, remember, I can have a circle. Here's my diameter. Here's a chord. Okay? It doesn't necessarily make it look really close, but it doesn't. I mean, this one didn't, but in 12, are they equal? BC and CD, those have to be equal because it shows that it's perpendicular and it's diameter. Okay? And then, like I said, we did the number once earlier. Let's see, I think the algebra's in the 7. Yeah. I get to the other part that has the algebra. I should just made this whole one. I don't know why I did. Should do that differently. Now, as you flip that over, you get to a little bit of the algebra around like 22-ish. Okay. If I get towards 22 in this case, we're solving for x. The only way to be able to solve for x in a case like this is what would you have to do with those? Yes, sir?
Here.
So they're equal to each other.
You just needed one? Sorry. Counting to 10 is really hard. I was missing. What's that? Why? The only way you can solve it. It's the only way you can solve it. Okay. Again, the math here is going to be really simple. Subtract and add. And you get 3. On the other side, though, That's where things can get a little bit dicier as far as, especially when you look at number 2. What shape is inscribed in that circle? It's a square, okay? So when you have a square, you know you've got 4 right angles and you have 4 sides that are congruent. Right? Now, if I draw that, it does 2 things. It's a diagonal of the square, and it's one of the circle. Diameter. Okay? And chord to the right. So, what does it do to the circle then? Cuts it in half. So how many degrees are in a circle? So what does it do to that then? Makes it 180. Now, do you have 2 chords that hit the 180? What does each one of those arcs have to then equal? I'm meaning like MJ and JK. These will have to be 90s. Okay. There's another reason why this happens is if I drew the other one in, remember how these become isosceles right triangles? 45, 45, 90. That's my central angle. There's my arc. There's a bunch of ways of showing that. Okay? On the one I just gave you, I'd like you to do the evens, please. Okay? The one I just gave you, front, back, evens, there's like maybe a dozen of them. All right? Go ahead and knock that out. This should not be real tough. Tomorrow we'll do some of the other trickier ones. We're going to do the Pythagorean theorem thrown in, and having to draw extra chords and pieces and radii and stuff like that. Today I thought I'd keep it pretty easy and go just with numerical stuff and go off to that. Okay? Shouldn't be so bad.